We'll try this one more time. When we start to look at Lewis dot structures, we're going to look at today at intermolecular attractions and bonding. And so the first thing we need to do is we need to create some Lewis dot structures. And if you notice, I've taken magnesium. It has 2 valence electrons, and so I've drawn in my 2 blue valence electrons there. And chlorine is going to come along. It has 7 valence electrons, and so you'll notice this red one creating that bond between magnesium and chlorine. In actuality, they don't really share. What's going to happen is magnesium is going to acquire or lose actually both electrons, 1 to each chlorine. But we want to look at this structure of magnesium with these 2 electrons. Now, if we go to boron trifluoride, boron has 3 valence electrons, 1 for each bond. And carbon has 4, and so it bonds to 4 hydrogen. Nitrogen has 5, and there's a pair of electrons on top, and that's going to be kind of important to this next conversation. And then we have 3 hydrogens all attached there. Water has 6 valence electrons. There's 2 unshared, in other words, unbonded pairs of electrons. And then last but not least, we have this carbon dioxide. And what happens is those 4 valence electrons of carbon, each of them are shared twice with the oxygens. And so what we're going to do is we're going to start looking at what's called a Vesper formula. And a Vesper formula, I'm going to erase this one real quick and give you a recap. But what a Vesper formula is, if we look at magnesium chloride looks like this and has these, chlorine has those valence electrons surrounding it. And what we're going to do is we're going to identify an X, a central atom, and so we're going to call this magnesium A. And this is just a generic formula for this valence shell electron pair repulsion. Now, pairs of electrons don't really like each other. I mean, you have these 2 negative charges pushing away from each other. And so what we get is we get this central atom A, and then we have 2 X's on either side, in other words, these 2 chlorine. And so this guy's actually called an AX2. And so we get this bonded, and you actually have only 2 pairs of electrons pushing away. Now we move over to boron trifluoride. It's got 3 pairs of electrons in bonds around it, so you get an AX3. And carbon follows suit with 4 pairs of electrons bonded to 4 things, and we get an AX4. Now here's where it changes a little bit. We have nitrogen in the center, and it's got 3 things bonded, but it's got a pair of electrons. And if we look at the title here, valence shell electron pair repulsion. So really we have 4 pairs of electrons repelling each other. But what we're going to do is we're going to identify the 3 atoms that are attached, so that gives us the X3. And the last thing that we need to identify is we need to identify that pair of electrons on top. So we get an AX3E, and that E identifies those pair. Let's move down to water. We have oxygen in the middle, that's our A. We have 2 hydrogen, those are our X's, so this gives us the AX2. But we also have 2 pairs of electrons, so we're going to call this E2 for those 2 pairs. Move over to carbon dioxide. We have 1 central atom. We have 2 things bonded, and we have no other pairs of electrons on the central atom. So it actually gives us this AX2 shape similar to magnesium chloride. Okay. What that does for us is by identifying what's called the Vesper formula, we actually are able to figure out geometries. And these geometries, as we look at them, AXs, if you bond 2 things only, you always get something that's linear. Okay, so we're going to look over here at the linear shape. If you bond 3 things and there's no extra electrons, so like our magnesium chloride, we get an AX2, we also get a linear shape. And the carbon dioxide also follows that suit. We'll skip over the AXE because that's back to linear. But we get down to like the boron trifluoride that we had on the last screen. We have boron in the center where we have 3 things bonded to it. And so what we get is actually this triangle shape, so we'll call it trigonal planar. And moving on, we have an AX2E, so we have 2 things bonded, but we have this pair of electrons that pushes those 2 angles down, and we get this bent shape. And moving on to the AX4, like our carbon with our 4 hydrogen on it, which is methane, we get an AX4. it is a tetrahedral shape, and what happens there is you get this little base triangle on it, and then what we're going to do is draw the outside atoms, and this is a really poor drawing, but we get this tetrahedral shape that's actually created. An AX3E, and that's our NH3, because we have an extra pair of electrons sitting on top of it. We get those pair of electrons push down those other three, so it can't be square, or it can't be trigonal planar. And so what we get is we get this little trigonal pyramidal. It actually kind of stands up on three legs. And so if you can think of this in three dimensions, we get these three legs, those hydrogens coming off each side, and the nitrogen sitting up on top, and that pair of electrons that are pushing them down. And example of water, AX2E2, we have these two X's, and these pair of electrons again are pushing, and you get this bent shape again between our XA and our X. And so we're back to a bent shape. And by knowing some of this information, we're actually able to tell what molecules might be polar, what molecules tend to not be polar. And so the next section is to talk about the polarity. And this is just a quick slide on what those molecules might look like if we were to stop and check them out. So we'll come back and talk on polarity in just a second.